Hello there, and welcome to the Whispering Science, where the wonders of the universe unfold softly in the gentle silence of the night. You've joined me on an exploration tailored for curious minds easing into slumber. Tonight, our focus drifts far across the known universe, farther than any telescope can peer, into the realm of black holes. Now, I do hope this isn't too interesting that it keeps you awake, but if it does, well, at least you'll have learned something fascinating about one of nature's most mysterious and powerful phenomena, the black hole, with its gravity so intense that it shapes not only space and light, but even time itself. Before we begin, if you enjoy these slow science journeys, I'd be ever so grateful if you tapped the like button, subscribed, or even just left a comment telling me where in the world you're watching from and what time it is in your corner of the night. Your thoughts, your presence, and your wonder are what make these explorations so special. So, settle in, get comfortable, and let's begin our quiet voyage into darkness and discovery, a realm where stars end and where the fabric of the cosmos seems to fold in on itself. Black holes may sound fierce, but tonight, through gentle science, we'll find that even the most extreme forces in the universe offer a kind of cosmic beauty and a reminder of how closely the universe's story is intertwined with our own. As the world softens around you and the edges of day dissolve, let the intricate tale of black holes lull you calmly, softly into a deeper understanding and perhaps into restful sleep. Black holes, perhaps you've heard the name whispered in documentaries or spotted it in headlines when the universe decides to reveal another of its wonders. But what exactly is a black hole? In its simplest explanation, a black hole is a region of space where gravity is so strong that nothing, not even light, can escape its pull. Imagine a place so gravitationally intense that the ordinary rules we follow, how light moves, how time ticks forward, how matter exists, are all transformed by one simple fact: the immense concentration of mass within a very small space. It's helpful to first picture what we mean by gravity. Every object with mass, your body, the chair beneath you, entire planets and stars, exerts a pull on everything else. Our Earth, for instance, holds you tight to its surface, so tightly that even when you jump as high as you can, you always fall back down. Now picture something billions of times heavier than our planet, but packed into a region smaller than the city where you live. Take that concept and fold it, step by gentle step, until you have a gravitational field so powerful that not just you, not just molecules, but even light, the fastest traveler in the cosmos, can never break free once it gets too close. The black in black hole hints at this reality. It's not just dark. Dark implies you could shine a flashlight and see something. Instead, a black hole is truly black because light, upon crossing a certain boundary around it, cannot escape to the wider universe again. No information, no signal, no image can reach an outside observer from within. It's as if the universe draws a curtain saying, what happens here stays here forever. Yet despite this formidable reputation, a black hole is not a cosmic vacuum cleaner, nor is it some mystical tear in space. It's an object with mass. And if you were to orbit it from a safe distance, you'd find it pulls on you with gravity in just the same way as any other massive object would. If suddenly, and let's emphasize suddenly, because in reality this could never just happen, our sun turned into a black hole of the same mass, Earth would continue orbiting at the same distance, just as always. Only the sun's warm light and familiar glow would be gone, replaced by a silent, invisible sphere. How do black holes form? We'll linger on this whispered question soon, but for now, know that black holes are not just cosmic garbage disposals. They're exquisite endpoints in the lives of massive stars, and, as we'll explore, key characters in sculpting galaxies and the flow of time itself. To bring this down to a more human scale, the idea of a point of no return, which black holes enforce with uncompromising clarity, isn't so foreign to our own world. There are places, imaginative or real, where, once you step across a certain threshold, things change irrevocably. In a black hole's case, that place is called the event horizon, the invisible surface where, if you cross it, escape is mathematically impossible. Let's pause and appreciate what makes black holes such a fascinating object to scientists and dreamers alike. They contain the universe's ultimate extremes, the greatest densities and gravitational pulls, the most dramatic warping of space and time, and maybe most exciting of all, the deepest mysteries that modern physics cannot yet untangle. They blend the fabric of Einstein's relativity with the finest particles and fields described by quantum theory, yet utterly confound both. And incredibly, black holes aren't just fantasy or speculation. Scientists have found strong evidence for their existence, both in the brilliant flashes of light emitted as matter spirals into them, and in the way their gravity governs the movement of entire stars and even galaxies. Some black holes are born from the deaths of stars. Others may have existed since the universe was young, and some lurk as monstrous giants at the heart of galaxies, including, as astronomers have deduced, the very galaxy we call home. So, what is a black hole? It's a cosmic region where gravity is the organizing principle, where light itself bows and vanishes, where the known laws of physics are tested to the breaking point. Yet beyond all that, a black hole is a scientific triumph of prediction and discovery. From their existence to their effects, we have learned, measured, and proven more about them than almost any other cosmic mystery. Surrounded by gentle darkness tonight, let your mind rest easy knowing that these places, so strange, so silent, are being patiently uncovered, hint by gravitational hint, by astronomers and physicists around the world. As we explore further, you'll see how understanding black holes also means understanding the universe's history, its fate, and even a little bit about yourself. Gravity is both a force you feel every day and the invisible hand that shapes the largest structures in the universe. Tonight, let's draw the curtains a little wider and step softly into gravity's domain. For understanding gravity is the surest way to see why black holes exist and how they transform their surroundings. Since earliest childhood, you've known gravity as what gently tugs you back to the ground, lets apples fall from trees, and gives weight to your body. But in the wider cosmos, gravity becomes the master sculptor, collecting dust and gas into planets, gathering planets into solar systems, and binding billions of stars together to make galaxies. Sir Isaac Newton was the first to mathematically capture this universal dance over 300 years ago in 1687. His law of universal gravitation explains that every mass attracts every other mass, with a force that grows stronger as objects get closer and larger, but weaker as they drift apart. This is why the Earth orbits the Sun rather than drifting away, and why the Moon circles the Earth, raising tides in our oceans as it does. But Newton saw gravity as a force acting at a distance. To him, it simply pulled objects together through empty space. For hundreds of years, Newton's view worked brilliantly. Ships navigated seas, planets traced their patterns, and engineers dreamed of journeys beyond our world, all guided by the equations he left behind. Then, in the early 20th century, Albert Einstein revealed a deeper layer of the story. In his general theory of relativity, published in 1915, gravity wasn't a force sent across empty space, but a bending of the very fabric of space and time. Dense objects like planets, suns, and, most powerfully, black holes create dents or curves in this cosmic fabric. When the Earth orbits the Sun, it's not being pulled by an invisible hand, it's moving on the straightest path through curved space, like a marble circling the dimple in a stretched-out sheet. As you lie there, you can imagine this cosmic fabric, soft and elastic, spread beneath the stars. Place a bowling ball on its surface, that's your Sun, warping space-time around it. Nearby pebbles, representing planets, feel the slope and roll around the main mass. But place something denser still, a star squeezed 1,000-fold or more, and the depression grows deep, steep, and eventually, as we'll learn, becomes a chasm so profound that nothing within it can escape. Such is the sway of gravity. It's infinitely patient, taking millions and billions of years to draw together the raw ingredients for stars, then shaping those stars' fates. The clouds you see in the Milky Way are immense piles of gas and dust, cold and thin beyond imagination. But over time, gravity's persistence pulls them denser, tighter, until eventually the crush becomes enough to ignite the nuclear fires at a star's heart. From here, a star's story unfolds, born of gravity's caress, living by its balance, and in the end, transformed by its final, inescapable grip. Black holes mark the climax of this story, a place where gravity's pull has run away with itself. Whereas the Earth's gravity is strong enough to keep an atmosphere, and the Sun's is enough to hold a solar system, a black hole's gravity is so profound it prevents even light, universe's swiftest messenger, from leaving. This is why, at the heart of every black hole story, we find gravity's invisible hands shaping destinies. But gravity isn't just about stars and black holes. It governs you in ways subtle and intimate. Every heartbeat, every subtle shift in posture answers to gravity. The distribution of fluids in your body changes a little with every step, and even your sense of up and down is granted by the gentle but ever-present tug of gravity through your vestibular system, deep within your ears. When you stand, your heart works harder than when you lie here softly, because gravity requires it to lift blood up to your brain. As your eyelids flutter, consider for a moment gravity's ceaseless role. It draws water up through tree roots and fills rivers from the mountains. It governs the tides, predictable, gentle, persistent, moving enormous masses of water on regular schedules that have ordered life on Earth for eons. The tides that made life's emergence possible, that still shape ecosystem cycles, are but one echo of the wider cosmic ballet orchestrated by gravity. And gravity is not just a passive background presence. It is the reason things fall together, sometimes gently, like morning dew sliding from a petal, and sometimes with dramatic finality, as in the last moments of a star's life, hurtling toward collapse. Black holes, which are not so much objects as they are regions of space where gravity has triumphed totally, stand as silent, powerful reminders of gravity's ultimate potential. So as we prepare to trace the path of a star's life and see how gravity shapes its destiny, pause a moment to notice gravity's patient presence in your own life. It holds the covers snug around you, tucks the pillow beneath your head, and connects you physically to the very ground, and through that, to the entire Earth spinning soft in the night. Our journey into black holes is really a journey into gravity's deepest secrets. To truly understand black holes, you first need to follow the slow, luminous journey of a star. Imagine, if you will, the beginning of everything. A cold, dark cloud of gas and dust drifting softly in the vast arms of a galaxy. Invisible, almost weightless, these clouds linger for millions of years, perfectly content to hang silent in deep space. But gravity is always at work. Slowly and gently, its invisible hand pulls denser pockets of matter toward themselves, cradling them until they become massive enough for something extraordinary to occur. As more and more hydrogen gathers, the temperature deep within these clouds rises, eventually reaching more than 10 million degrees Celsius. At these extreme depths, the immense pressure causes atoms of hydrogen to fuse, creating helium, and in the process, releasing a spectacular burst of energy, starlight. This marks the birth of a star, just as our own sun began its life some 4.6 billion years ago. From this moment, gravity and energy act as perfect opposites, locked in an eternal gentle tug of war. Gravity squeezing in, crushing from all sides, while the heat and light from fusion pushes outward, resisting collapse. A star spends the vast majority of its life in this tranquil balance. For billions of years it shines, a soft nuclear engine steadily producing the energy that will someday nurture planets, light up night skies, and even make life possible. Throughout its life, a star's fate is written into its mass. The larger the star, the grander the spectacle that awaits at its end. Our sun is considered a medium star, and when its fuel is finally spent, it will expand, shed its outer layers gently into space, then settle as a quietly glowing white dwarf. No drama, no dazzling final bow. But if a star is much, much larger, at least 8 times more massive than our sun, it is destined for a far more dramatic ending. These giant stars burn their fuel with wild intensity, lives measured not in billions, but millions or even just a few 100,000 years. Their cores become layered like an onion, building heavier and heavier elements, until finally the core is mostly iron, and there are no more nuclear reactions left to squeeze any energy out. Here, quietly, gravity wins at last. Without the gentle outward push from nuclear fusion, the iron core can no longer support its own weight. In a fraction of a second, gravity causes the core to collapse inward, compressing matter to unimaginable densities. This collapse triggers a core collapse supernova, a cataclysmic explosion that blows the outer layers of the star out into space, briefly outshining entire galaxies. The supernova scatters stardust across the cosmos, seeding future generations of stars and even planets, including the elements that make up everything in your body, the iron in your blood, the calcium in your bones. Yet, what remains at the very center after the supernova's fury is nothing less than astonishing. If the collapsed core's mass is between about 1.4 and 3 times that of the Sun, it becomes a neutron star, a dense, city-sized ball of neutrons with truly extreme gravity. But if it is even heavier, gravity's win is absolute. No known forces can resist the crush, and the core continues collapsing, shrinking past every known limit until it forms a black hole, a point in space where the material is so tightly concentrated that the escape velocity exceeds the speed of light. At this stage, a new black hole is born. Its gravity is so strong that it curves space-time to a breaking point, creating an event horizon, the ultimate boundary. The matter and energy from the fallen star are compressed and hidden forever, leaving behind only mass, spin, and electric charge to interact with the universe. Physicists call this the no-hair theorem. From outside, all black holes look nearly identical, except for these 3 simple properties. A black hole may start small, but as we'll learn later, it can continue to grow by swallowing anything that drifts too close. A stray star, a cloud of gas, even an entire planet. Most black holes that form from stars, what we call stellar black holes, are about 3 to 10 times the mass of the Sun. Their size is minuscule compared to their mass. A black hole 10 times the Sun's mass is only about 60 kilometers wide, not much more than a large city. The death of a massive star may seem like a quiet loss for that patch of space, but in truth, it is the universe's grand recycling process. The elements cast off in a supernova explosion can someday end up in planets, moons, and life forms, perhaps even in you and me. And deep in the darkness left behind, the black hole begins its long, silent existence, its gravity shaping the fates of everything nearby. So as you float closer to sleep, know that every black hole is the result of a cosmic story as old as time itself. A cycle of birth, radiance, and peaceful collapse, all choreographed by the subtle artistry of gravity. Somewhere, right now, new stars are being born, their future black holes already written in the stars, promising to continue the beautiful, quiet rhythms of the universe for billions of years ahead. Let us slip even deeper into the heart of this cosmic tale and rest gently on the question: how does a giant star become a black hole? You might picture a star as a constant, unchanging beacon, but in truth, stars are dynamic and sometimes unstable, their lives driven by ongoing battles between gravity and the energy from nuclear fusion. For massive stars, the finale to this long battle is unparalleled in its intensity, a dramatic death that begets one of the universe's strangest objects. As we softly recalled, a star shines because nuclear fusion in its core creates outward pressure, perfectly balancing gravity's inward pull. While a star has plenty of lighter elements to fuse, this balancing act is smooth and serene. However, when a very massive star, 8 or more times the Sun's mass, nears the twilight of its life, its store of fusion fuel changes. After countless millennia of fusing hydrogen to helium, it starts fusing heavier elements in succession. Helium to carbon, carbon to oxygen, oxygen to neon, and so on, all the way to iron. Iron is unique because fusing it doesn't produce energy. It does the opposite. It demands energy, turning the core into an energy sink rather than a source. The star is betrayed by the very process that once allowed it to shine. With nothing left to oppose gravity, the core begins an abrupt collapse. In less than a second, the core shrinks from a sphere the size of the Earth to a sphere just a few kilometers across. Atoms are squeezed so tightly that electrons and protons merge into neutrons, and a fierce, bright flash called a supernova signals this downfall to the universe. But if the collapsing core is above a critical mass, somewhere above 3 solar masses, according to current theory, Even the strong force binding neutrons together cannot stop the collapse. Gravity overcomes all known resistance. The core plummets inward, crushing itself into something smaller and denser than anything else in the cosmos. At this point, something extraordinary happens. Space and time become so steeply curved within this shrinking sphere that light itself cannot escape. This is the birthplace of an event horizon, a one-way invisible surface encircling what has become a new black hole. Anything that passes within this boundary, be it gas, light, or even time, is lost to the rest of the universe. Nothing returns, nothing escapes. The event horizon marks the edge. From the outside, you never see the core reach a point. Instead, to a distant observer, it appears to slow, redden, and freeze in place, forever hidden by the laws of relativity. This endgame defies intuition. If the core is about the mass of our sun, it might become a neutron star, so dense that a sugar cube-sized piece outweighs Mount Everest. But if it's heavier, further collapse becomes inexorable. Its mass shrunk into a region no bigger than a city. Vertigo sets in as you realize this. Every familiar law of physics, motion, matter, the ticking of time, becomes radically transformed in the final moments of collapse. It is here that astrophysicists focus their most patient attention. The precise journey from collapsing core to black hole involves matter accelerating to fractions of the speed of light, temperatures soaring to billions of degrees, and gravity twisting space so tightly that, in the end, what remains is just its gravitational influence on the outside universe. Even the light from the supernova, which can for a moment outshine an entire galaxy, is a soft whisper of the violence occurring within. You might wonder, how do we know this actually occurs? In 1967, Jocelyn Bell Burnell discovered the first pulsar, a rapidly spinning neutron star sending regular flashes of radio waves toward the Earth. This was the first direct evidence that stars really could collapse that far. Black holes, being even darker and more secretive, left their mark in the sudden X-ray flashes noticed by astronomers in binary star systems, the last breaths of matter spiraling into an invisible companion. It's humbling to consider that every atom heavier than hydrogen you encounter, perhaps in the air you breathe or the blood in your veins, was forged in the last moments of some long-lost star, its death witnessed across light years by the universe itself, and somewhere its core may have slipped so silently through that final boundary, birthing a new black hole whose gravity will linger long after the supernova fades from view. Every black hole represents a victory of gravity over all the other forces that shape the cosmos, an ending so profound that it is famous even among the most distant galaxies and ancient civilizations. You, curled up now and drifting towards sleep, are connected by lineage to these cosmic events. The calcium in your bones and the iron in your blood come from the hearts of stars, one or two of which may have ended as black holes, their light now gone, their history softly recorded in your very body. So the next time you look up at the night sky, remember, a handful of those pinpricks of light are stars destined in time to meet this magnificent hidden fate. In the velvet darkness above, the process is constant, ongoing, and utterly serene against the expanse of time. With the gentle unveiling of a black hole's birth, let us draw nearer to one of the most intriguing mysteries, its strange geometry of mass, size, and the boundary known as the event horizon. When you think of an object in space, you might imagine its surface, something solid like the crust of the Earth or the visible outer layer of the Sun. But a black hole has no such traditional surface. Instead, it presents us with the event horizon, a kind of mathematical boundary rather than a material shell, marking the point around the black hole where escape becomes impossible. Imagine you're floating with serene curiosity near the dark heart of a black hole, observing from a safe distance. The event horizon is the spherical invisible border that perfectly encircles the core of the black hole. Its radius depends solely on one thing, the black hole's mass. For a non-rotating, uncharged black hole, physicists use a formula called the Schwarzschild radius to define this. If a black hole's mass is equal to our Sun, the event horizon would form a sphere just about 3 kilometers wide. For a black hole 10 times as massive as the Sun, the event horizon would rest at about 30 kilometers from its center. Compared to the size of the original star, the black hole's dimensions are astonishingly small. This region is not just a theoretical curiosity. The event horizon is an absolute threshold. You could imagine it as the ultimate cosmic point of no return. Once anything, a photon of light, a bit of cosmic dust, even time itself, crosses over this threshold heading inwards, it cannot come back. No force, no amount of energy, not even the light speed dash of a photon, can reverse its course past this veil. All of the information about what has fallen in, apart from mass, spin, and charge, is effectively erased from the outside universe. It's soothing to picture. From a very great distance, a black hole may seem just like any other source of gravity. If the Sun, for example, were magically replaced by a black hole of the same mass, Earth would still orbit at the same distance. The real wonder is not in their external gravity, but in the way they compact so much mass into such a tiny volume. Here's an awe-inspiring comparison to help you unwind into restful contemplation. Imagine if all the humans on Earth were squeezed into a single sugar cube. That's the kind of density you find inside a black hole, except even denser. With every new addition of mass, the event horizon bulges outward, gently expanding to keep pace. The space inside the event horizon is something our minds have trouble wrapping around. Time and space cease to behave as we expect. Distances and intervals become warped by the nearness to ultimate gravity. To an outside observer lingering far away, anything falling into a black hole appears to slow ever more, its light stretched to red, fading until it winks from sight. But for the object itself, crossing the event horizon is uneventful. No dramatic signs, no sudden force, just a surreal, inescapable glide deeper toward the core. It's important to note that everything beneath the event horizon becomes truly hidden, sealed off from the rest of the cosmos. No signals, no traveling particles, no observations can be made of what happens underneath. In this way, black holes introduce a sort of cosmic censorship. The secrets within are kept perfectly, and the only evidence of the matter or energy that went in lies in the black hole's own mass and, in more complex cases, its spin and electric charge. Physicists often describe the outside of a black hole as extremely simple. From a distance, you could never tell if the matter that made the black hole was part of a star, a planet, or something stranger. The black hole erases every distinguishing detail. Yet, this apparent simplicity hides a fascinating and ongoing debate in modern science about whether and how the information about what fell in might be preserved or lost, a mystery known as the information paradox. For now, the event horizon guards its secrets well, making black holes not just physical oddities, but reservoirs of cosmic mystery. So as you close your eyes and visualize the form of a black hole, recall this. It is a region where mass has been so concentrated that the boundary it creates, the event horizon, is less a surface and more an invisible casing around a mystery, a one-way gate beyond which neither matter nor light can return, defined only by mass, charge, and spin. The event horizon quietly changes the shape of space itself, warping it so steeply that all paths within lead inward. You and I cannot visit such a place, nor can our signals escape from within, but we can watch at a distance as the universe's drama quietly plays out along its boundary. It stands as one of nature's gentlest yet most absolute rules. Beyond here, there is no return. We gently drift now, closer to the enigmatic core of the black hole, where reality's rules as we know them lose their familiar shapes and meaning. At the very center, hidden beneath the event horizon, lies what physicists call the singularity. The singularity is not a place in space in the way we normally think about a location. Instead, it's the ultimate point of collapse where all the black hole's mass is thought to be squeezed into zero volume and infinite density. Here, the mathematics of our beloved physics seem to shudder and break down entirely. To understand the singularity, first imagine the gravity near a black hole's center, growing stronger the deeper you go beneath the event horizon, increasing by unimaginable orders of magnitude with every shrinking centimeter. As you approach this core, The fabric of space and the rhythm of time are twisted beyond all recognition. Einstein's equations that so elegantly describe the curves and folds of space-time do not yield any further. Instead, they lead to answers that are simply undefined, infinity, zero, and mathematical nonsense. This is how physicists know they've arrived at a frontier in our understanding. The singularity is an endpoint in a journey that began with stellar collapse, as we explored. All the mass from the progenitor star and anything that has since fallen in is believed to concentrate at this infinitely small spot. Density rises sky high, even more than in the dense neutron star phase, and space-time itself folds tightly around it. Yet, for those outside the event horizon, there is no way to view or probe the singularity directly. Its presence is inferred by the black hole's gravity and the laws of Einstein's general relativity. The laws of physics are like a carefully woven tapestry, strong and reliable most of the time, but the singularity is where the threads are pulled so tight they unravel. Quantum mechanics, the set of rules that explains how things work on the smallest scales, says matter shouldn't be able to be packed into a single point. Meanwhile, general relativity claims that at the very center, the gravitational field becomes infinitely strong. These two worldviews, both brilliant in their own domains, conflict violently at the singularity. This stark contradiction is not just a puzzle, but a guiding star for modern physics. Scientists suspect that, at such extremes, our current knowledge is incomplete. Something deeper, perhaps a unified theory of quantum gravity, must reconcile the known laws and reveal what truly lies at the heart of a black hole. Many researchers hope that one day, black holes and their singularities will provide the laboratories, albeit ones beyond our reach, that inspire this grand unification. From a peaceful vantage far away, you might wonder, does the singularity have a size? In classical models, it is a perfect point, zero width, no surface, just a looming end to physics itself. But theories exploring quantum effects hint that things could work differently. Perhaps the singularity is replaced by an object with some quantum size, a fuzzball of tangled space and time. Or perhaps the collapse bounces, emerging elsewhere in another universe, or even forming the seed of a new cosmos, theoretical, awe-inspiring ideas all, but for now, unanswered questions. Historically, the concept of the singularity began to crystallize in the 20th century, alongside the maturation of Einstein's theories. In the 1960s, Roger Penrose and Stephen Hawking, two diligent and imaginative physicists, used the mathematics of general relativity to prove that once a massive star collapses past a certain point, the formation of a singularity, at least in theory, is inevitable. Their work won international recognition, shaped the global science community, and touched off decades of rich inquiry into the mysteries deeper than the event horizon. As we rest on this idea tonight, it's comforting to realize that even the universe's darkest places can serve as sources of insight. Black holes do not simply represent ends, but also beginnings for new ideas and discoveries. The singularity stands as a signpost, one that says, here is where the map ends. Beyond this, new wonders must surely lie. So as you settle in and let your mind explore, know that the singularity isn't just a frightening abyss. It's also an invitation for discovery. It humbles every scientist and thinker who tries to unlock the universe's most hidden truths. Yet it also sparks imagination, inspiring generations to look deeper, dream bigger, and search patiently for tomorrow's answers. Perhaps one day, a future scientist, maybe even a listener softly falling asleep tonight, will peer beneath the curtain of a black hole and gently illuminate what really lies within. Resting in the gentle shadow of the singularity, let's explore a perspective that may surprise you. Black holes are not just cosmic consumers, silently swallowing everything in their path. Instead, recent science has revealed that black holes play essential, even creative roles throughout the universe. These mysterious objects are not merely endpoints. They shape the galaxies around them, influence cosmic evolution, and help forge the environments that allow stars, planets, and even life itself to arise. For much of the 20th century, black holes were imagined as little more than traps, places where information energy and matter met an inescapable doom. But astronomers and astrophysicists, aided by new telescopes and technologies, began to suspect another possibility. They noticed, for instance, that at the cores of most large galaxies, including our own, the Milky Way, there are supermassive black holes, millions or billions of times more massive than our Sun. In some galaxies, these giants seem to govern the fate of the entire system. How does this shaping occur? Consider a galaxy in its youth, a whirling disk of gas and dust, illuminated by newborn stars and flickering with the promise of stellar birth. In the very heart of this cosmic city, gravity gathers material so rapidly and in such dense quantities that a supermassive black hole forms. As material spirals toward it, enormous energy is released, a brilliant beacon known as a quasar, or active galactic nucleus. These engines outshine their entire galaxy for millions of years, their intense radiation and jets of particles heating up vast clouds of gas, and sometimes even blowing them out of the galaxy entirely. This powerful feedback regulates the galaxy's evolution, halting star formation in some regions and igniting it in others. Black holes, then, don't simply gulp down matter. They govern how much material is available for new stars and planets, creating cycles of birth and dormancy across hundreds of thousands of light years. The Milky Way's own supermassive black hole, Sagittarius A*, rests quietly at the moment, but evidence from elsewhere shows these cosmic hearts can flare into prodigious activity when fed enough gas and dust. But the influence doesn't end there. As black holes merge and grow, they stir the very structure of their galaxies, pulling stars into new orbits, reshaping the distribution of matter, and sometimes even ejecting stars into intergalactic space. Without the gravitational anchors provided by supermassive black holes, most galaxies might never have formed their elegant spiral arms or maintained their luminous disks for billions of years. On a smaller scale, stellar mass black holes left behind by dying stars can be the centerpiece of cosmic dramas as well. When paired with ordinary stars in binary systems, they become voracious, feeding on the atmosphere of their companion star, heating it until it glows with X-rays detectable from across the galaxy. These X-ray binaries were among the first places astronomers found convincing indirect evidence of black holes. Black holes also create environments where the laws of physics are tested more fully than anywhere else in the entire universe. Disks of gas swirling around the event horizon reach temperatures of millions of degrees, emitting copious amounts of energy and sometimes launching jets of matter at nearly the speed of light. Scientists use these natural laboratories to probe how matter behaves at the extremes, from the richness of general relativity to the puzzles of quantum effects. For human life, this might seem distant, yet there are surprising links. The gold in a ring, for example, and the heavy elements in your phone and computer are largely believed to come from mergers involving black holes and neutron stars, cataclysmic events that forge the periodic table's rarest treasures in a fraction of a second. In this way, black holes don't just take, they also help bring forth the very stuff we use and hold each day. Even at a cosmic level, the quiet action of black holes is essential to the grand balance of the cosmos. Consider that, without the energy and winds blown by feeding black holes in very young galaxies, too many stars might form, using up all the gas too quickly and ending the rich era of planet and life formation almost before it started. Black holes may impose a kind of cosmic moderation, ensuring galaxies remain lively, beautiful, and sustaining across cosmic timescales. It's easy to see now why scientists have shifted their perspective, from fear to fascination, from viewing black holes as dead ends to understanding them as sculptors, regulators, and sometimes even midwives of new cosmic opportunity. The universe is not a static place. It's a place of constant transformation, and black holes, in their silent darkness, are among its most powerful creators of change. So, as you continue to rest and let your thoughts settle, know that black holes are woven quietly into the fabric of cosmic evolution. Far from being simply destroyers, they are teachers, influencers, and shapers of everything from the orbits of distant stars to the atoms that form your world. Our continued exploration of black holes helps us appreciate a universe that is even more interconnected and dynamic than we ever could have dreamed. Floating gently now through the structures black holes shape, you might wonder, are all black holes alike? Or does the universe craft them in a wild array of sizes and types? Just as there are tiny pebbles and colossal mountains on Earth, the cosmos is home to black holes of astonishing diversity, ranging from the mass of a single star to monsters that outweigh billions of suns. Let's drift quietly through these cosmic extremes, discovering how black holes are classified by their mass and the company they keep. The most familiar black holes are known as stellar mass black holes. These are born from the deaths of massive stars, as we've softly explored, and typically weigh in at about 3 to perhaps a few dozen times the mass of our Sun. Imagine, if you will, all that weight squeezed into a sphere not much larger than a city, an object so compact that it could fit comfortably inside Manhattan, yet so heavy that not even light can resist its grasp. Stellar black holes are speckled throughout our galaxy. Scientists suspect there may be as many as 100 million or more lurking quietly, often invisible unless matter falls into them and flares with telltale X-ray signals. Larger still are the so-called intermediate mass black holes, a category that long remained mysterious. These black holes, weighing in between roughly 100 and 100,000 solar masses, seem to represent a missing evolutionary step between the smallest and the largest. Evidence for these mid-sized black holes is growing, found by studying the dense star clusters in distant galaxies and observing rare but powerful gravitational wave signals when they collide with other black holes. Still, their origins remain one of astronomy's gently nagging mysteries. Do they form from repeated mergers of smaller black holes, or from the collapse of enormous ancient clouds of gas? The answer remains softly out of reach, and then, in the swirling heart of galaxies, lie the titans of the cosmos, supermassive black holes. These truly giant objects tip the scales at millions or even billions of times the Sun's mass. Sagittarius A*, the supermassive black hole at the center of our Milky Way, is about 4 million solar masses, while others, like the black hole in the galaxy M87, reach 6 billion solar masses or more. Their event horizons are so vast they could comfortably contain our entire solar system, while their gravity shapes the orbits of hundreds of millions of stars. Unlike stellar black holes, these supermassive objects do not come from the simple collapse of a single star, but seem to have grown over cosmic time by gathering stellar debris, merging with other black holes, and perhaps collapsing directly from immense clouds of primordial gas. For decades, these monster black holes evaded even the most persistent astronomers. But with the rise of radio telescopes, X-ray observatories, and, most recently, gravitational wave telescopes, their monumental presence has become impossible to ignore. Their influence is written in the movement of stars and gas swirling in the centers of galaxies, and in the high-velocity jets that shoot from their poles, stretching across hundreds of thousands of light years. These are cosmic engines, sculpting galaxies and regulating star formation for billions of years. There are also whispers, still debated, about the possible existence of primordial black holes, hypothetical objects formed not from collapsing stars, but from dense knots of matter in the first instant after the Big Bang. If they exist, these black holes might range from the mass of a mountain to far more, silently drifting through space, and possibly providing subtle clues to the universe's earliest moments. Though none have yet been confirmed, the ongoing search for primordial black holes is a quiet frontier in the story of black hole research. What binds all these varieties together is their defining trait: the event horizon. Whether the black hole formed from a supernova, the merger of ancient objects, or the collapse of vast clouds, it is this perfect boundary, this one-way surface from which nothing can return, that marks it unmistakably as a black hole. The difference is in their scale, from city-size to planetary to solar system-spanning giants, each with a gravitational signature written clearly across the fabric of space. Just as humanity's ancestors looked up at the sky to find patterns among the stars, today's astronomers read the universe's structure by tracing the forms, sizes, and whispers of black holes. Our telescopes and detectors can now see their effects, even when light itself is lost to the event horizon. Each discovery adds another gentle piece to the cosmic puzzle, painting a richer and ever more interconnected story of how black holes of all sizes knit together galaxies, clusters, and the cosmos itself. As you ease further into comfort, let your mind wander across the universe's tapestry of black holes, a continuum from star-sized shadows to galactic hearts, knowing that in their diversity, the story of cosmic evolution becomes more beautiful and complex. The universe is not confined to simple repetition, but instead crafts an array of wonders, differing in scale, yet united by the strange grace of gravity's embrace. Now, as you let your breathing settle and drift deeper, let's gently reveal that even among black holes of the same size, not all are exactly alike. While every black hole, no matter how massive, is wrapped tightly by an event horizon, some possess more subtle varieties, spinning swiftly about their axis or holding a trace of electric charge. These differences, though invisible to our eyes, create a delicate diversity among black holes and add another layer of fascination to nature's most mysterious objects. To begin, let's imagine a non-rotating, uncharged black hole, the simplest kind, known in physics as a Schwarzschild black hole. Its event horizon is perfectly spherical, and its defining properties are its mass and nothing more. This model forms the serene foundation of black hole theory, but the universe rarely crafts such idealized forms. Most black holes, scientists believe, are spinning. When a massive star collapses, any rotation it has is preserved and concentrated in the resulting black hole, a consequence of the physical law called conservation of angular momentum. Because the collapsing core's size shrinks so drastically, any small initial spin grows immensely as the black hole forms, similar to how a figure skater spins faster when they pull their arms close. A spinning black hole is called a Kerr black hole, after physicist Roy Kerr, who first described its shape in 1963. These black holes can spin at incredible speeds, near the maximum allowed by the laws of physics. In fact, if you stood safely outside a fast-spinning black hole, you'd find the very fabric of space around the event horizon is twisted and dragged along with the spin. This effect, called frame dragging, means that space and time are not quite the same near a spinning black hole as they would be near a still one. The event horizon bulges at its equator, and just outside it there lies a region called the ergosphere. Here, objects can be swept around faster than anywhere else in the universe, so fast in fact that energy can, in theory, be extracted from the black hole's rotation. Some black holes might also possess electric charge. These are called Reissner-Nordstrom black holes if they don't spin, or Kerr-Newman black holes if they both spin and have charge, while it's unlikely for real astrophysical black holes to carry much charge. As the universe is extremely efficient at neutralizing excess electrical imbalances, the mathematics of these objects has helped physicists probe what happens when black holes interact with quantum fields, charged matter, and cosmic rays. Charged black holes introduce complex inner structures, like two different horizons and possible temporary safe zones between them, all defined and predicted by the delicate equations of general relativity. The diversity of black holes isn't just an academic curiosity. Rotating and charged black holes allow us to explore the very extremes of physics. Their spinning ergospheres have inspired theories about cosmic particle accelerators, while their different horizons offer insights into the fate of matter and information at the edge of the universe's most haunted boundaries. As we study the X-ray signals or gravitational waves emitted by matter swirling into these dynamic black holes, we piece together their inner structure from afar, decoding the signatures of spin and even hints of charge. Spin also has practical effects on the universe around the black hole. Powerful jets of plasma, observed in distant galaxies and even our own, are thought to be launched by gigantic magnetic fields entwined with the spin of supermassive black holes. These jets can shoot out for hundreds of thousands of light years, carrying energy away and sculpting the intergalactic medium. The behavior and power of these jets, and the way gas swirls inwards in flattened disks, depends strongly on how quickly the black hole is rotating. It might feel a little abstract, but there is a delicate poetry in this diversity. Just as no two snowflakes are structured alike, no two black holes spin quite the same, and each becomes a focal point for the drama playing out in its celestial neighborhood. The way light bends, the motion of nearby stars, and the flickering signatures observed by telescopes. In each, astronomers are quietly reading differences in spin, charge, and mass that betray the true nature of these invisible giants. As you lie quietly, you can sense how science finds beauty even in the subtlest differences. Every black hole, whether still or spinning wildly, is an intricate solution to the equations of general relativity, a unique stamp of gravity's ultimate artistry. And as research continues, every new observation whispers fresh details about the diversity, dynamism, and enduring mystery of these cosmic shadows. So, as your mind gently reviews tonight's discoveries, recall that even in the darkest places, variety flourishes, spinning out new tales in the fabric of space-time, proving that the universe, like a master composer, never runs out of ways to surprise us with the richness of its silent music. Let's float now along the river of history, tracing the quiet footsteps of discovery that brought black holes out of pure mathematics and into the realm of real, observable phenomena. It may surprise you to know that the journey began not with telescopes or space probes, but with thoughtful equations and a touch of creative imagination. The idea of a star so dense that not even light could escape dates back more than 2 centuries, to the work of British natural philosopher John Michell in 1783. He envisioned dark stars that could trap light, but at the time, the wave theory of light and the nature of gravity were so poorly understood that his idea faded quietly into the background. More than 100 years later, in 1915, Albert Einstein would revolutionize our thinking with his general theory of relativity, a new framework for understanding gravity, not as a force, but as a curvature of space and time. Just a year after Einstein's breakthrough, a young German physicist named Carl Schwarzschild solved his complex equations for the first time, almost as a mathematical curiosity, describing the peculiar properties of what we now call a black hole. His solution revealed the existence of an inescapable surface at a certain radius, the event horizon. Yet for decades this was considered a mere oddity, a solution never thought to exist in nature. After all, what force could compress so much mass into so small a space? For years, black holes were the stuff of pure theory. It wasn't until the 1930s that the discovery of the neutron star, another product of stellar collapse, provided a taste of the extreme. Physicists like Subramanian Chandrasekhar and J. Robert Oppenheimer quietly realized that given enough mass, nothing known could stop gravitational collapse. Yet, even then, the term black hole did not exist. It was only coined in 1967 by physicist John Archibald Wheeler, giving a powerful new name to this mathematical shadow. But how did black holes pass from equations to observable reality? The key lay in looking for invisible partners in the sky. In the late 1960s and early 1970s, astronomers using X-ray telescopes scanning the heavens found mysterious flickering sources like Cygnus X1. These luminous signals seemed to come from areas where no visible light betrayed a normal star, suggesting something small and incredibly massive was consuming matter from a companion star, heating it and causing matter to spiral inwards with a feathery blaze of X-rays. Careful measurement of orbits and energy flows led to the stunning conclusion. These objects were black holes, the very shadows once thought to be fantasy. The story did not stand still. Over the next decades, as telescope technology advanced, astronomers accumulated more candidates, stellar mass black holes in our galaxy, and supermassive black holes lurking in the centers of distant galaxies. Indirect evidence emerged in the behavior of stars swirling at impossible speeds, in the twinkling X-ray binaries, and in the elaborate high-speed jets streaming from the hearts of galaxies. A dramatic leap came in 2015, when the LIGO Observatory in the United States detected for the first time gravitational waves, gentle ripples in space-time generated as titanic black holes merged over 1 billion light-years away. These signals, so faint yet so precise, matched exactly what Einstein's equations had predicted for merging black holes. Humanity had, for the first time, heard the sound of black holes colliding, a true confirmation that these were not just tricks of mathematics, but real actors on the cosmic stage. And so, from bold theoretical beginnings through decades of skepticism, black holes have become among the most studied objects in modern astronomy. Each discovery builds on the last, echoing the work of unsung mathematicians, curious philosophers, and generations of scientists looking up at the night sky and wondering if darkness itself could be a source of light for our understanding. As you relax deeper, consider the patient way science unfolds. Black holes are the ultimate example of a journey that began in the quiet mind, leapt from pen and paper, and now, through the ingenuity of humanity, can be traced by the gentle flashes of X-rays, the eddies of swirling stars, and even the soft whisper of gravitational waves traveling undisturbed across all of cosmic history. All of it, each step, has brought us closer to seeing and knowing these luminous shadows for what they truly are. Profound mysteries waiting quietly behind the stars. Close your eyes and let your thoughts drift to one of the most extraordinary moments in recent science, when humanity managed, for the first time, to see the shadow of a black hole. For centuries, black holes evaded our telescopes, observable only by their gravitational effects on light and matter nearby. But in April of 2019, the quiet suspense of waiting gave way to a collective gasp of wonder as the Event Horizon Telescope collaboration unveiled the first ever image of a black hole's silhouette. This achievement was not simple luck, nor was it the result of a single new gadget. Rather, it was the patient fruition of decades of planning, innovation, and perseverance. Scientists across the globe coming together, each contributing a gentle brushstroke to this cosmic portrait. The subject? The supermassive black hole at the center of galaxy Messier 87, often known simply as M87. This leviathan, about 55 million light-years away in the Virgo cluster, possesses a mass equivalent to more than 6.5 billion suns and an event horizon larger than our entire solar system. But how do you see something that is, by definition, invisible? The solution is as ingenious as it is elegant. Rather than direct imaging in visible light, astronomers turn to radio waves. The Event Horizon Telescope, or EHT, is not a single telescope, but a planet-spanning network of synchronized radio dishes. Stations from the mountains of Hawaii to the plains of Spain, from the South Pole to the deserts of Chile, worked as one, using a technique called very long baseline interferometry. This allowed astronomers to achieve a resolving power thousands of times sharper than even the Hubble Space Telescope, enough to discern something the size of a grapefruit on the moon from Earth. The result was an image embedded in your memory, even if you've never gazed at it deliberately. A softly glowing ring of light encircling a pitch-dark center against the backdrop of the distant universe. That glowing ring is not the black hole itself, but the bright inner edge of a disk of superheated gas swirling at nearly the speed of light. The dark center, the so-called shadow, marks the event horizon's boundary, the last point from which light can escape. It is, in essence, the silhouette of the invisible, traced by the light it consumes. To bring this image to life required not just technology, but stunning patience and coordination. The EHT observations spanned years, collecting petabytes of data, so much in fact that it was faster to ship hard drives by airplane than to transmit the bits digitally. Teams of scientists spent months developing algorithms to piece together the image, remove noise, and account for the blurring effects of our own atmosphere. Just as a long exposure photograph allows faint stars to reveal themselves in a night sky, the EHT's careful synthesis allowed the black hole's shadow to be revealed at last. For many scientists and laypeople alike, this image was a wow moment, a concrete visual touchstone for one of the most abstract concepts in nature. It was not just the culmination of Einstein's predictions or support for the existence of event horizons. It was a triumph of human curiosity, creativity, and perseverance. The image, now displayed in classrooms and coffee shops around the world, serves as both proof and poetry, a reminder that even the oldest, darkest secrets of the universe are not beyond our patient, gentle reach. In years since that first image, scientists have also begun unveiling pictures of our own galaxy's supermassive black hole, Sagittarius A asterisk, building a new era in black hole studies. With each image, the world of these enigmatic objects grows more tangible for all of us. The shadows become less void and more like signposts, guiding us to deeper understanding, paths illuminated not by what is seen, but by the patient sleuthing of invisible light and the unity of a global scientific community. As you lie back and let your mind drift, picture the gentle effort of humanity banding together, spanning continents, transcending language and time, just to glimpse the silent heart of a distant galaxy. Even when exploring the blackest regions of the cosmos, science finds a way to bring a quiet, luminous glow to the edge of the unknown, turning shadows into knowledge, mystery into wonder, and cosmic silence into a shared story written softly across billions of light years. As the night deepens and our minds grow ever more tranquil, consider the invisible fabric that wraps all cosmic objects together, a fabric not made of threads, but of space and time itself. Think of this as you might think of a soft, invisible field stretching everywhere, effortlessly supporting planets, stars, and galaxies. It is the very essence of Einstein's general theory of relativity, space-time, a single interwoven entity where space and time are gently blended and through which all things move and age. To truly understand how black holes warp reality, it helps to imagine this space-time as a kind of flexible sheet. Place a marble on it, and the sheet sags ever so slightly. Place something heavier, like a bowling ball, and the depression deepens. Nearby marbles roll inward, following the curved slope. In our universe, the bowling balls are planets, suns, and especially black holes. When a black hole is present, the sheet is pulled so steeply that you cannot walk back up the slope, no matter how much energy you have. A perfect metaphor for the event horizon, that boundary of no return. In Einstein's elegant vision, gravity is not a mysterious, invisible force pulling objects together from a distance, as Newton suggested. Rather, gravity arises because mass and energy tell space-time how to curve, and the curvature of space-time tells mass how to move. Every object, even you lying quietly now, makes a tiny dent in this cosmic fabric. Our bodies, the planet beneath us, the sun in the sky, they all softly stretch or compress space-time in their own ever so delicate ways. But a black hole formed from matter enormously compressed into an infinitesimal region doesn't just make a gentle dip, it creates a cavern, plunging space and bending time so dramatically that ordinary motion and even light itself must follow strange looping paths. This warping becomes especially pronounced near and within a black hole's event horizon. Imagine the paths that light can take, which in empty space would travel straight and swift. Near a black hole, those paths bend, curve, and sometimes circle endlessly in the so-called photon sphere, a halo where light can orbit the black hole like a planet orbits the sun. Further in, all paths curve inward until eventually none can lead away. Light, time, and matter all are drawn inexorably toward the singularity. One of the profound consequences of this extreme curvature is the phenomenon known as gravitational time dilation, where time itself moves differently for observers at different distances from a massive body. This effect is gentle on Earth. You might age a tiny fraction of a second less in a valley than atop a mountain, an effect only the most precise clocks can measure. But near a black hole, this becomes so powerful that time for an observer hovering just outside the event horizon slows to a crawl compared to someone farther away. When space is warped, so too is time. The closer you approach a black hole's edge, the more the seconds stretch, the more the tempo of clocks slows, and the more the outside world seems to rush on, leaving you forever behind. This isn't science fiction. It's a real prediction of Einstein's equations, confirmed in the delicate ticking of atomic clocks flown in airplanes or perched on mountaintops, and dramatically evident around black holes. Historical experiments have demonstrated that massive objects alter time's flow. The Hayfel-Keating experiment in 1971 sent atomic clocks on commercial airplanes and compared them with clocks left on the ground, finding the predicted difference in time elapsed. This gentle slowing of time is almost imperceptible in everyday life, but around black holes, the effect grows overwhelming. In the most extreme case, The singularity at a black hole's heart halts the passage of external time completely, locking everything within to an unchanging fate. So as you drift in your mind along the curves and folds of universal space-time, appreciate that the warping of space and time is not an abstract curiosity. It's the real framework through which black holes wield their power and shape the stories of matter, light, and life itself. And every moment you spend here, feeling the slow hush of night, the movement of the world beneath you, the swirl of stars above, you are nestled softly within space-time's vast, silent embrace, sharing in the cosmic rhythm that black holes so dramatically reveal. Now let's journey together, softly, into one of the most spellbinding effects that black holes have on the universe: their power to bend not only space, but the fabric of time itself. This profound phenomenon is called time dilation, and to truly appreciate its wonder, let us begin with a gentle moment of imagination. Picture yourself holding a perfectly precise clock, one that counts the passing of each tick with unfailing regularity. On the surface of the Earth, this clock keeps time as expected. But as you approach a black hole, your movement through time itself begins to gently, inexorably shift. Unlike science fiction's fanciful time machines, this is a real and measured effect, predicted by Einstein's general relativity and confirmed through experiment. Time dilation occurs whenever you enter a strong gravitational field, and nowhere is gravity more intense than near a black hole. The reason lies in the warping of space-time. Imagine time as a ceaseless river. Out in open space, far from any massive object, this river flows smoothly and steadily, every second indistinguishable from the last. But as you draw close to a black hole, the river of time begins to slow. At first, the change is subtle, but near the event horizon, time's current becomes a mere trickle. Let's anchor this idea with a concrete example. Suppose an astronaut, let's call her Mia, decides to hover near the event horizon of a stellar mass black hole, while her friend Arjun remains far away, observing Mia from a safe distance. With powerful thrusters, Mia keeps herself just outside the event horizon's edge. To Arjun, watching through a telescope, time appears to slow terribly for Mia. Her movements become sluggish. Her clock ticks more and more slowly compared to his own. What seems like hours to Mia might be years, centuries, or even millions of years to Arjun, depending on how close she floats to the event horizon. This stretching of time isn't limited to thought experiments. Thanks to the extreme gravity at the event horizon, the mathematical equations tell us that, right on the boundary, time actually stands still with respect to the outside world. If Mia were to send a message, her last words would appear to freeze, stretch to infinity, never to reach Arjun at all. The very concept of now becomes twisted by gravity. Near a black hole, what is present for one observer might be the distant future for another. It's not just clocks and messages that are affected. Light too changes character as it struggles to escape, its waves stretched longer and redder, a phenomenon astronomers call gravitational redshift. Light emitted outward from just above the event horizon becomes stretched to longer and longer wavelengths, eventually slipping into oblivion, invisible even to the keenest detectors. As time slows for the sender, so too does the frequency of light, a poetic demonstration of the union between time and space. The gentler manifestations of time dilation occur all the time, right here on Earth. The clocks on your GPS satellites tick ever so slightly faster than clocks on the ground, because those satellites are further from Earth's gravity well. Without adjusting for this difference, the navigation on your phone or in your car would quickly wander hundreds of meters off course. Einstein's insight into time dilation, refined and tested with technologies you use every day, reminds us that the warping of time is not just buried deep in space, but part of our living, practical world. But near a black hole, this effect grows profound, so profound that fictional stories and films like Interstellar have played with the idea of astronauts experiencing just hours on a planet near a black hole, while many years fly by elsewhere. The fundamental physics is accurate. Gravity can create such drastic differences in the pace of time when its embrace is strong enough. Time dilation is not only a scientific marvel, but also a deeply humbling reminder of how the universe's most basic elements, space and time, are fluid, not fixed. They respond to mass and gravity, and nowhere more majestically than at the boundary of a black hole. To gaze upon a black hole from afar is to look into a place where time, quietly and gently, has been slowed almost to a halt by the embrace of perfect gravity. So, as the night deepens around you and you listen to the steady rhythm of your own heart, let yourself pause and reflect on time's patient river. You are connected via the gentle thread of relativity to the grandest clocks in the cosmos, the galaxies and black holes whose unseen hands shape eras and guide the pulse of eternity. Even as you drift towards sleep and tomorrow, remember, in the universe's darkest places, the story of time is quietly and profoundly different. Let your body relax further as we gently imagine. What would it truly feel like to approach the edge of a black hole? Not in the language of dry equations or computer simulations, but as an intrepid astronaut, quietly gliding closer to the event horizon, the enigmatic border where neither matter nor light can ever return. Let's picture yourself in a sturdy spacecraft, carefully navigating toward a stellar mass black hole. Far from this ultimate abyss, things are deceivingly calm. Black holes themselves emit no light, unless surrounded by swirling, glowing disks of heated matter called accretion disks. If your black hole is feeding, you might see a brilliant whirl of X-rays and visible light, forming a glowing halo around a perfect dark center. But imagine approaching a quieter, isolated black hole, with only starlight and the infinite night as your companions. At first, nothing seems amiss as you drift closer. Gravity grows stronger, pulling with a force beyond any planet or star you've ever encountered, yet your ship's engines compensate, keeping you on course. The star field ahead warps, subtly at first, then ever more dramatically. Due to the intense curvature of space-time, the distant stars and galaxies appear bent and stretched around the black hole, as if you're peering through a cosmic funhouse mirror. Behind you, the rest of the universe compresses into a small, bright circle. This isn't an illusion, it's the real bending of light, where the black hole's presence acts as a gravitational lens, focusing the glow of the cosmos into strange halos and arcs. As you approach the event horizon, time slows, not only externally, as felt by the observers you left behind, but in a way that becomes eerily perceptible. Your ship's clock ticks its normal pace from your perspective. Your thoughts come as usual, but if you could see a live video feed from your friends far away, they'd appear to move in hyperspeed. Messages you transmit would be received at an ever-slowing rate, and replies would come less and less frequently, stretched thin and pale by the deep red shift near the horizon. Closer still, the difference becomes extreme. To an outside observer, you appear to crawl ever more slowly, taking longer and longer to approach the invisible border. Your colors redden, your image dims, and you freeze in time. To you, however, there's no drama as you cross the event horizon, no sudden jolt, no bump. General relativity says you glide smoothly through, unless the gravitational tides are unmanageably severe, something we'll whisper about soon. If the black hole is supermassive, like those found in the hearts of galaxies, the event horizon might be millions of kilometers wide, and the journey across could be surprisingly uneventful. The immense scale means the tidal forces, the difference in gravity between your head and your feet, are gentle where you cross. You might only sense the darkness growing absolute, the last snatch of outside light spiraling across the horizon, forever lost. All the while, you continue falling inward to the unfathomable singularity, your clock still ticking, but forever cut off from the outer universe. If, however, you attempt this feat near a smaller stellar mass black hole, the crossing is anything but peaceful. There, the gradient in gravity, from your feet to your head, grows so enormous that it would pull you apart in a process chillingly known as spaghettification, which we'll soon discuss in soothing detail. Being at the edge of a black hole is more than a journey through space. It's a journey into an alien realm of physics, where every step closer brings reality deeper into the folds of relativity. If you carried a flashlight and tried to shine it outward, its beam would spiral around the black hole, robbed of all hope of escape. Should you attempt to hover just above the horizon, the force required to stay still would soar, quickly surpassing the thrust of any conceivable engine, making all resistance futile to gravity's claim. It's poetic in its quiet certainty. To the universe, the event horizon is the dividing line between what can be known and what is lost. Your friends watching from afar would see you approach the edge, slow, fade, and hang in time, never truly witnessing you slip away as your final signals redshift into darkness, stretched infinitely. From your perspective, you experience the journey with unbroken continuity, crossing the event horizon with no more sensation than passing a speed limit sign, an unmarked border into the eternal night. So, as you lie here nestled in comfort, let your thoughts explore gently. In the universe's deepest wells, the laws of nature conspire to create not horrors, but astonishing vistas of warped light, slowed time, and the most profound boundaries of existence. No human has made the journey, but armed with math, imagination, and care, we can all take that voyage softly as the ultimate cosmic explorers. Lie back even further and let's conjure gently, with scientific care, the extreme and almost surreal fate that befalls anything drawn too near a stellar mass black hole, a process known, perhaps misleadingly soothing, as spaghettification. Despite the softly whimsical name, this is one of nature's most dramatic demonstrations of gravity's power, an effect where the differences in gravitational pull are so intense that objects are stretched and thinned into long, slender strands resembling spaghetti. To understand why this happens, recall that gravitational force is stronger the closer you are to the source of gravity. In normal life, on the surface of Earth, there's a slight difference in the pull of gravity between your head and your feet. So slight you don't even notice it. Yet near a black hole, this difference, called a tidal force, becomes anything but gentle. As you fall feet first toward a stellar mass black hole, the gravity at your toes is much, much stronger than at your head, even if the two are only separated by a meter or so. The reason for this lies in the compactness of the black hole. In a stellar mass black hole, only a few times more massive than the Sun, the curve of space-time grows so steep near the event horizon that even small differences in distance mean enormous changes in gravity's strength. If you were to fall in, the gravitational pull at your feet would accelerate them toward the center of the black hole faster than your head. At the same time, gravity compresses you from the sides, squeezing you into the thinnest strand of yourself, ever stretched thinner and thinner the closer you approach the singularity. This process accelerates rapidly. The tidal forces just outside the event horizon of a small black hole are so powerful that they would begin pulling apart even molecular bonds, separating the atoms, then subatomic particles, until all structure dissolves into a near-perfect line of fundamental matter. The stretching is not just a vivid image, it's an inescapable result of the mathematics of general relativity. Scientists have calculated that a human-sized object would be torn apart long before crossing the event horizon of a stellar mass black hole, the process unfolding in mere seconds. Yet, as we touched on softly before, if the black hole is supermassive, millions or billions of times the Sun's mass, the tidal forces at the event horizon are surprisingly mild. The event horizon is so far from the center that the difference in gravity across a human body is small. In such gigantic black holes, you could, at least in theory, cross the event horizon without immediately noticing a thing, only to meet your inescapable fate much closer to the singularity deep inside. Spaghettification may sound fanciful, but its underlying principle is everywhere in the universe. Tidal forces from gravity shape moons, create ocean tides, and even heat distant worlds like Jupiter's moon Io so violently that they become volcanic. Here on Earth, our tides rise and fall because the moon pulls more strongly on the side of Earth facing it than on the far side, a soft, daily echo of the same principle that spells destruction near a black hole. Famed physicist Stephen Hawking often remarked on the strange beauty of these extremes. The very violence of spaghettification is also a pointer to one of the universe's most fundamental truths. Where gravity is left unchecked, its effects are absolute. The process is not gruesome or vengeful, it's simply the logical outcome of physical laws, played out beyond our world's gentle limits. There's a tranquility, even in this unraveling, a return to fundamental particles and energies that continues, perhaps, into new cosmic cycles. On a more gentle note, the stretching and squeezing that define spaghettification are studied by scientists as they observe flares and disruptions in star systems near black holes. Sometimes, a star will venture too close to a supermassive black hole and be torn apart, producing brilliant and brief flashes that reveal clues to the processes at work. These observations not only confirm the theory, but also give us a window, fleeting but real, into the inner workings of these cosmic laboratories. As you rest now, think of spaghettification as the ultimate illustration of how gravity, distance, and motion intertwine in the depths of the universe. It's the final whisper of matter's structure, giving way before the ultimate force, a process as much a part of nature's tapestry as the formation of stars and galaxies, as intrinsic to the universe as the gentle tides that move our own seas. Know, too, that you are safe from these extremes. Black holes are so far, so rare, and the night sky is broad and welcoming. Your body, held together by earthly gravity and the bonds of matter, rests securely. But by contemplating this dramatic stretching, we glimpse nature's most secret powers, witnessing, from the comfort of our own gravity well, the silent, spectacular logic that shapes the universe's deepest shadows. Let your breathing grow calm as our exploration brings black holes gently closer to home, connecting their immense gravity and strange effects to your everyday life and your own body. It might seem that black holes, hidden in remote corners of the galaxy, have nothing in common with the rhythms of your heart or the passage of your days. But the truth is quietly more wondrous. Black holes and the forces that forge them are built from the same universal law, gravity, that shapes your world, your movement, and even the very chemistry inside you. Gravity may seem subtle as it safely hugs you to the earth tonight, but its reach is unbroken. The iron in your blood, for instance, was created in the fierce heart of an ancient star, one that may have ended in a spectacular supernova and perhaps left behind a black hole. Every time your heart beats, it pumps that iron-rich blood throughout your body, linking you to the life and death cycles that black holes complete on the grand cosmic stage. The calcium strengthening your bones, the oxygen you breathe, the carbon building your cells, all assembled from atoms born in stellar furnaces, many under the titanic pressures that only gravity can provide. Each second you experience is governed by the flow of time, moving at a pace set by the strength of gravity. It's easy to forget, but time's flow isn't uniform across the universe. The gentle tug of gravity at Earth's surface makes time pass a tiny bit slower than high above the ground, an effect so minute it's only measurable with the most precise atomic clocks. Yet this same effect, writ large near black holes, brings about the dramatic time dilation we described. That's why, as you rest here, legs, arms, and mind equally influenced by gravity's pull, your experience of now is a small version of the cosmic story being played out around black holes. Your relationship with space-time may also be more personal than you think. The satellites that guide your phone's navigation rely on clocks so accurate they must be corrected for the difference in time passage due to Earth's mass, a direct, gentle echo of the way black holes reshape time. Even a task as easy as standing up in bed is your body quietly working against gravity, a process that's gentle here, but unbeatable in the fierce grip of a black hole. The black holes that sculpt galaxies and regulate star birth do so at a level of scale and distance that's hard to fathom, but their very existence provides the heavy elements and the gentle lessons about time and physics that make our everyday experience possible. You are, in a very real sense, made of star stuff, matter that once drifted in clouds and may have passed close to black holes, or even through the supernovae that create them. Every breath and every heartbeat links you with the cosmic cycles of creation and destruction. Black holes also remind us how small differences in gravity's strength, almost imperceptible on Earth, become magnificent forces over cosmic distances. When you gaze up at the stars, you're not just looking at distant lights, but at the ongoing history of gravity sculpting everything, from swirling nebulae to spinning galaxies. Black holes are the intense punctuation marks in this narrative, shaping space, bending time, and locking away matter to mysterious futures yet undiscovered. Imagine for a moment that the room around you were to suddenly double in mass. Time would move just imperceptibly slower for you, in accordance with gravity's influence, a miniature version of what happens at the event horizon of a black hole. While no such change occurs in the quiet of your bedroom, it's a gentle reminder. The structure of your world and the passage of your life are quietly bound to the same cosmic laws that govern black holes. So as you float further into relaxation, let the thought comfort you that you are a product of gravity's patient sculpting, a child of the same universe that spins out black holes, nebulae, and galaxies by the million. The forces that seem remote and unfathomable are, at their core, the same ones that cradle you on Earth, whispering of a universe that is interconnected, beautiful, and in its way, deeply personal. Allow yourself to rest even deeper now as we gently turn to one of the modern wonders of black hole science. The way these enigmatic entities serve as cosmic laboratories, places where nature's deepest laws are put to the ultimate test. Although black holes are unreachable for direct experiment, from afar they provide more than enough clues. Like great silent teachers, they allow scientists to probe ideas and forces at the very edge of our understanding, opening windows into realms that can never be reproduced in any earthly laboratory. Black holes stand at the crossroads of the universe's great theories. On one side lies Einstein's general relativity, describing gravity and the shape of space-time with elegant precision. On the other waits quantum mechanics, the theory governing the behavior of the tiniest building blocks of matter and energy. In nearly every other corner of science, these two theories work independently, rarely stepping on each other's toes. But within and near a black hole, both must be considered simultaneously. Yet, our current understanding has not fully stitched the two together. This makes black holes the perfect testing ground for new theories of quantum gravity, which might someday unite all of physics under one harmonious description. Scientists study the regions around black holes with all the tools at their disposal. Powerful X-ray, radio, and gravitational wave telescopes look for signals from matter spiraling inward at relativistic speeds, from jets of particles ejected along the black hole's poles, and from the colliding mergers of black holes themselves. Each signal brings information about how matter and energy really behave in the extreme, where density, gravity, and temperature reach heights unmatched anywhere else in nature. For example, the accretion disks around some black holes spin so quickly and are compressed so tightly that the atoms inside them experience conditions far beyond any on Earth. As electrons are stripped away from atoms and atomic nuclei collide at incredible speeds, they emit characteristic flashes of X-rays, a cosmic fingerprint for scientists to decode. These signals help scientists test whether Einstein's equations hold true under the most punishing conditions, or if subtle differences hint at new, deeper laws waiting to be discovered. The detection of gravitational waves by LIGO and Virgo collaborations, beginning in 2015, marked a turning point in our ability to use black holes as laboratories. When two black holes spiral together and merge, they send out ripples in the fabric of space-time itself, disturbances detectable after traveling billions of years as the tiniest changes in the distance between mirrors on Earth. These observations confirm predictions made nearly a century ago, and also test relativity in regimes where gravity is strongest, validating Einstein's theory with a gentle confidence unmatched elsewhere. Black holes also offer unique insight into the so-called information paradox, a deep scientific mystery posed by Stephen Hawking. When matter falls into a black hole, does any trace of the information about its original state survive, or is it lost forever? In everyday life, we take for granted that information can be preserved in some way. But black holes seem to erase everything except mass, charge, and spin, challenging the fundamentals of quantum theory, which insists that information must always be retrievable somehow. Ongoing studies, from Hawking radiation to string theory and beyond, are slowly peeling back this paradox, with black holes as the ever-patient teachers. What's more, black holes are cosmic engines. In their accretion disks and jets, they generate some of the most powerful outbursts of energy known, far outshining entire galaxies forging heavy elements, and influencing the birth of stars over millions of light years. As scientists observe these processes, they are in effect watching nature perform experiments at scales and energies impossible to create on Earth. By decoding these cosmic experiments, astronomers learn about magnetism, turbulence, high-energy particles, and perhaps even the earliest conditions of the universe. You, too, are a participant in this scientific adventure. Every gravitational wave detection, every black hole image, every flash of X-rays from a distant binary system does not just belong to scientists in quiet control rooms, but can be witnessed, celebrated, and understood by anyone who gazes up at the night sky with wonder. Our ability to use black holes to test the universe's most fundamental rules is a reminder that we are not isolated from nature's vast laboratories, but quietly connected to them, learning through patient observation and the persistent power of curiosity. So as you relax, know that the universe's most extreme places, black holes, are not just boundaries or ends, but beginnings. They are the extra-cosmic classrooms where both humanity and nature teach, learn, and gently test the rules that structure everything you know. Through their infinite patience, black holes invite us to contemplate, to dream, and to reach ever further into the silent, fertile unknown. As you breathe softly and sink deeper into relaxation, let us explore the lingering mysteries that black holes hold, questions that inspire scientists around the world, even as they cradle our deepest sleep with possibility. For all the breathtaking discoveries and breakthroughs, black holes remain at the very frontier of human knowledge. Each answer they reveal seems to whisper back a new riddle, as if the cosmos is gently inviting us to keep exploring, to keep dreaming. One of the greatest mysteries still unsolved is the true nature of the singularity hidden within each black hole. As we softly discussed, conventional physics predicts an infinitely dense point where the known laws of space, time, and matter break down. Yet, such infinities are a signpost, not a destination, a sign that our theories are incomplete. What truly happens in the depths, where gravity is overwhelming and space-time is twisted beyond measure, remains cloaked by the event horizon. Are singularities real, or does a new, as yet unknown theory smooth out the extremes, perhaps with quantum effects that transform the sharp core into something more complex? The answer is a treasure scientists continue to gently seek. Another enduring mystery arises from the information paradox. Stephen Hawking's discovery that black holes can emit radiation, now called Hawking radiation, suggests that black holes can slowly evaporate over time, shrinking and ultimately disappearing. But what happens to the information about everything that once fell in? Does it vanish, violating the core tenets of quantum mechanics? Or is it mysteriously encoded into the radiation that escapes? This paradox, debated for decades, remains unresolved, but has sparked new fields of study at the edges of relativity and quantum physics. The exact origin and growth of supermassive black holes, the titans living at galaxy centers, remain shrouded in cosmic history. Did they form directly from the collapse of massive gas clouds in the early universe? Or did smaller black holes merge and grow eon by eon, fed by rivers of interstellar matter? Recent observations of quasars, galaxies ablaze with the brilliant emission from feeding black holes, show that some supermassive black holes grew extremely large very early in cosmic history. How did they gather so much matter so quickly? The mechanism remains a source of gentle puzzlement and thrilling discovery. There is also the ever-intriguing question: do primordial black holes exist? These would be relics from the universe's first moments, born not from stars but from density fluctuations in the hot plasma after the Big Bang. If even a few endure, they might help explain the elusive dark matter that makes up much of the cosmos, or offer clues to the very foundation of the universe. So far, evidence is tantalizing but incomplete, leaving astronomers to keep watching, waiting, and hoping. Black holes may even conceal new laws of physics altogether. The search for a unified theory of quantum gravity, one that unites the smooth, continuous world of relativity with the granular, probabilistic world of quantum mechanics, may find its solutions in the heart of black holes, or in the subtle signals they emit. Some theories propose that singularities open tunnels to other universes, or that information is woven into the very fabric of space-time at the horizon's edge, in a structure sometimes referred to as a firewall or a hologram. Closer to our own time and place, scientists still puzzle over precisely how black holes interact with their environments, how they launch jets of matter across galaxies, how accretion disks become unstable and erupt, and how pairs of black holes dance and merge, sending ripples of gravitational energy into the cosmos. These phenomena illuminate new physics at every turn and challenge us to invent ever more sensitive instruments to listen and watch. Every question lingering about black holes shapes the future of science. Some mysteries will quietly persist for generations. Others may be answered suddenly, in a future flash of insight or a new signal captured in the gentle hum of gravitational waves. The adventure is ongoing, inviting everyone, however near or far from the science, to share in the wonder. As you gently surrender to sleep's embrace, take comfort in knowing that the universe is still full of mystery. Black holes, in their silent darkness, are not brick walls in the story of knowledge, but doors, quietly open, beckoning, bathed in the promise of yet undiscovered truths. Even now, as your mind prepares to slip across the threshold of dreams, the cosmos is whispering new puzzles, waiting for the next eager dreamer to listen, to learn, and to illuminate all that still lies hidden beyond the event horizon. And now, as the vast journey through cosmic darkness brings us to our quiet close, let us drift gently into the afterglow of everything you've learned tonight about black holes, their anatomy, their mysterious births, their places in the tapestry of the universe, and the way they warp the very nature of time. Just as the soft hush of night falls around you, black holes lie silently in the universe, guiding galaxies and shaping destinies, visible only where they touch the world with gravity or cast their shadow against the glow of surrounding stars. We've traveled softly through stellar death and rebirth, watched stars collapse and singularities form, and marveled at how even the strongest force in nature leaves space for wonder. Black holes, those cosmic shadows, teach us about extremes and boundaries, but they also illuminate how deeply connected you are to the universe. The iron in your blood, the gold on your ring, even the seconds as they pass around you, each bears the silent mark of the same processes that build and sustain black holes. Every gentle heartbeat is an echo, across time and scale, of the great flows of energy that ripple through space, the same forces that arc around the event horizon's secret rim. As you rest deeper, remember that black holes are not only mysteries, but also cosmic sculptors, shaping galaxies, shaping time, and quietly reminding us that even in the deepest darkness, there is structure, law, and the enduring invitation to discover. You too are an explorer, bound by gravity to the earth but free, in mind and in dreams, to wander the universe's most astonishing realms. Tonight, you have traveled smoothly past the visible, touched by equations older than our planet, and stories written in the very first seconds of the universe's life. I'd still love to know where in the world you're watching from, and what time it is there. Your presence here is a quiet connection, a thread across time zones, bound by curiosity and a shared sense of awe. If these gentle science journeys have brought you comfort or sparkled your imagination, know that there's a whole universe of wonders waiting quietly for your next visit. And so, as we come to the end of our gentle journey, layer by delicate layer, we have peeled back the universe's shadows, finding in each a lesson about ourselves and our place in the cosmos. May the scientific stories you've learned tonight echo softly through your dreams, carrying you into sleep, wrapped in the peaceful knowledge that, even as black holes shape the stars, your own dreams help shape the next chapter of discovery. May you drift now into rest with gravity's calm hold, feeling perhaps a little more at home in this vast, marvelous universe. Good night, and may you dream in starlight and the gentle curves of space-time, where every question is a doorway and every shadow a hidden promise, softly waiting to be revealed.